The theory of a prehistoric cosmic explosion, often called the Big Bang, is widely accepted by most scientists as the primary explanation for the creation of the universe, including the creation of stars, planets, and all life. Despite its somewhat unusual name, the term Big Bang aptly describes the enormous importance of the event. In the beginning, the universe was a dense collection of particles compressed into a space smaller than the head of a pin. From that moment, there was a huge explosion of matter known as the Big Bang, which condensed the interactions that had developed over billions of years. Despite the continued popularity of the Big Bang theory, advances in science increasingly cast doubt on its predictions. When NASA launched the James Webb Space Telescope, JWST, the largest and most advanced space observatory to date, scientists expected that its observations would confirm the Big Bang theory. Unfortunately, after only 1 year in space, the telescope amazed scientists with its remarkable capabilities, providing extraordinary insights into the universe's past. JWST's discoveries have revealed systems so ancient that they may actually change our understanding of the origin of the universe. This unexpected revelation generated intense interest among researchers and hobbyists. One remarkable discovery came when astronomer Rohan Naidu analyzed early images of JWST by chance that the system took everyone by surprise. This galaxy, called Glass Z13, appeared mysteriously gigantic and dates from just after the Big Bang, making it older than any previously observed galaxy. Naidu's excitement was palpable as he shared the revelation with his colleagues on Earth, describing it more than astronomers could imagine. Located far from natural disturbances and equipped with state-of-the-art technology, the James Webb Telescope was created to study the earliest eras of the universe, known as the Cosmic Dawn. This mysterious period marks the formation of the first stars and galaxies in the universe. By studying systems from this era, scientists hope to improve their understanding of key cosmic cycles, such as the effects of matter and dark energy. Initial expectations for the JWST findings were modest, expecting only a few faint, distant galaxies. However, the reality exceeded all predictions, because the images obtained by the telescope revealed systems with amazing development, which challenged existing models and led to the result of the analysis. As scientists continue to dissect the JWST data, the implications of these revelations could be profound and usher in a new era of cosmological understanding. The surprising discoveries of this remarkable observatory offer a fascinating glimpse into the past of the universe, encouraging humanity to try to unravel the mysteries of existence. As early systems came into being, researchers and viewers alike found themselves struggling to understand them. Could this cluster of unexpectedly large and bright early galaxies be the result of errors in the telescope's analysis of the original observations? Or, if they are genuine, can they somehow be reconciled with standard cosmological models? It's possible that the universe is stranger and more complex than our wildest speculations allow. At stake is nothing less than our understanding of how precisely the universe as we know it emerged from primordial chaos. The first findings of the James Webb Space Telescope can rewrite the early chapters of cosmic history. These numbers concern not only distant ages and distant galaxies, but also our own existence in the Milky Way. As Mark McCaffrian, the European Space Agency's senior science and research advisor on JWST, commented, "You don't build these machines to reinforce a worldview, you build them to break it. You just don't know how it's going to break." In some ways, JWST observations of early galaxies have been made for billions of years. But more subtly, they originate from the Space Telescope Science Institute in 1985. At the time, the Hubble Space Telescope was still 5 years away from launch, but the director of the institute at the time, Riccardo Giacconi, asked his team to think about what may come after Hubble in the much more distant future. Despite his focus on Hubble's successor, Giacconi was persistent and predicted a long development process. Garth Illingworth, then deputy director of SDSCI, began to develop ideas with a small team for what would later become the Next Generation Space Telescope, NGST, later renamed JWST. They realized that although Hubble was groundbreaking, its capabilities were limited by visible light observations. NGST, on the other hand, observes in the infrared region, which would allow it to look further into the universe. The need for JWST became even more evident in December 1995 when astronomers conducted the Hubble Deep Field observation. Despite expectations of finding only a few faint galaxies, the resulting image revealed thousands of galaxies stretching back more than 12 billion years into the cosmic past. After more than 20 years of development and a cost of approximately $10 billion, JWST finally launched on Christmas Day 2021. The telescope underwent extensive testing before it reached deep space a month later. By July 2022, it was ready to begin its much-anticipated first year of science observations, known as Cycle 1. Part of JWST's initial mission was dedicated to impressive programs, including early-release science for cosmic evolution and gravitational lensing. Amplified survey from space, both aimed to shed light on the mysteries of the early universe. When astronomers spent countless hours searching different regions of the sky for galaxies in the early universe, they initially expected modest findings that resembled a more detailed version of the Hubble Deep Field. However, they were shocked. Stephen Finkelstein of the University of Texas at Austin, who led the SEWIRS project, explained that the formation of very distant galaxies was expected only after several cycles of data from different projects. But to the surprise of astronomers, these galaxies formed very quickly. The record for the most distant known galaxy was previously held by GN Z11, discovered in 2015 at redshift 11. Redshift measures the stretching of light due to the expansion of the universe, with higher values indicating greater distance. But since glass observations began, two separate groups, one led by Rohan Naidu, independently detected glass Z13 at a redshift of 13.3, further altering the cosmic timeline. To obtain quick results, the researchers relied on redshift estimation methods based on luminosity measurements rather than time-consuming direct measurements. Despite their simplicity, these estimates showed that the galaxies are unexpectedly bright and massive, with some already having the stellar mass of billions of suns, similar to the Milky Way, which is billions of years older. The excitement didn't stop there. In the following days, many candidate galaxies appeared, some with redshifts estimated at 20, indicating that they existed only a short time after the Big Bang. These galaxies showed disk-like structures that were not expected for such early cosmic ages. Additionally, another team found evidence for smooth spiral galaxies at a redshift of 10, less than 500 million years after the Big Bang. The rapid formation of large galaxies challenges the expectations of the cosmological standard model, lambda cold dark matter, lambda CDM. To understand this anomaly, it is necessary to return briefly to the early dynamics of the universe in the moments after the Big Bang. The universe was a hot, dense soup of eternal particles. Over time, as the universe expanded and cooled, helium and other light elements formed, leading to the formation of the first atoms about 400,000 years later.
Approximately 100 million years after the Big Bang, conditions were favorable for the formation of the first stars, consisting mainly of hydrogen and helium. Those early stars, which are larger and brighter than today, were accreted into protogalaxies under the influence of dark matter. But the JWST discoveries challenged that model, revealing bright, massive galaxies much earlier than expected. Stacy McGaw of Case Western Reserve University noted the surprising absence of many smaller protogalactic components, suggesting that some observed galaxies may be closer than thought, obscured by dust, and appear fainter and more distant. The discovery of early galaxies raises important questions about the early stages of the universe, emphasizing the need for continued research and revision of our cosmological models. Follow-up glass Z13 observations from the Atacama Large Millimeter Array in Chile in August 2022 challenged the initial findings. Although ALMA used luminosity-based estimates, it did not detect significant amounts of dust associated with glass Z13. As noted by Paola Santini of the Tor Vergata University of Rome, who led the observations, low redshift culprits can be ruled out, but ALMA's failure to detect the galaxy highlights the challenge of confirming JWST's high-precision observations. One of the scientists involved, Rohan Naidu, noted the paradox of the situation, saying, "The good news is that nothing has been detected. The bad news is that nothing has been detected." Since only JWST can track its observations, the most worrying explanation may be that the standard lambda-CDM cosmological model needs updating. Cosmologist Michael Boylan-Colchin expressed the magnitude of this potential paradigm shift, saying, "These results are very surprising and difficult to reconcile with our standard model of cosmology. That would be a real revolution." To understand the problem, one controversial proposal is to modify Newtonian dynamics by questioning the existence of dark matter. The JWST observations may support the modified Newtonian dynamics, MOND, proposed by Mordecai Milgrom, although not all cosmologists are convinced of the validity of MOND. Another possible explanation is that early galaxies in the universe may have very little dust, making them brighter and affecting mass calculations. This scenario may also explain ALMA's difficulty in detecting glass, Z13. Charlotte Mason and her colleagues suggested that JWST could observe the brightest, young galaxies of the early universe, which could mean easier star-forming conditions during that era. David Spergel supports this idea, suggesting that the formation of high-mass stars could have been more efficient.